Yes, so you heard, I am Åström, a professor of environmental geology at Linnaeus University, and that is based in Kalmar, which is about 70 kilometers from here, so a very nearby university. And my area of expertise is chemical processes in the natural environment, and that is, of course, then what I will talk about today as well. Yes, it's 2 pages, and on both sides. So the presentation will focus on 2 kind of settings. The surface system, mostly surface waters, and then the deep system, that is chemical processes in the bedrock fractures. And the focus on the deep system is of course quite obvious. I mean, that is where the nuclear waste is going to be stored. However, also the surface system is important, because not until any radionuclides potentially leached from a repository enter the surface environment, they will cause a problem. So that's why we also need to understand what is going on in the surface system. Only in the surface system will any radionuclides produce problems. So also this first part of the presentation then about the surface system. And as you all know, surface waters look like this, more or less. River, a lake, stream, you all know that. Another kind of surface water which we have here is also wetlands. And these are quite common here up in the north, partly because of the cold climate, lot of precipitation, little evapotranspiration. A lot of these have been drained, but still quite a few of them. And soil groundwater can also be classified as surface system, at least in the context we are in. We talk about deep systems. When we do sampling of these surface waters, it can look like this. For example, here to the left, we are out measuring pH and electric conductivity. And in all kind of studies of natural surface or natural waters, we want to measure the pH. The pH is really a key variable when it comes to hydrochemical investigations, because it controls so much of the water chemistry, and it controls also the ecosystem, the biology. So pH is a really crucial parameter. So always when we do an investigation of waters, we more or less start with pH. We want to know, is it acid water, neutral, basic? It has so much influence on anything else. And it can be measured in the field, as is done here. Here we also measure electric conductivity. And that is actually a measure of total ionic charge in the water. That is the salinity, how salty the water is. That we can measure directly as well. So when we measure these two, we already know quite a lot of the water. The pH, and is it a fresh water, a salty water, or whatever. Of course, in most investigations of this kind, we want to do more than pH and conductivity. So here is a former PhD student going out in a canoe, taking some 10 liters of water for more detailed analysis. Nice. And here up in the north, we can also take advantage of the ice. As you can see here, it's perfect to sample on the ice. Of course, it can be a little bit cold. If it's minus 30, it's not so pleasant. But here it's sunny, a few minus degrees, 1 meter thick ice, just to dig a hole and collect a nice bottle of water. Here we are in an estuary, and that is the zone where the river meets the sea. and we have some heavier equipment. And this is especially convenient when we are sampling sediments. You can imagine to be in a boat, it's shaky and it goes here and there. This is absolutely stable, so it's just perfect to be on the ice. So sampling on the ice, especially in spring when it's sunny and nice, that is really great. So now, what are the characteristic features of surface waters in Sweden and Northern Europe? Are there any characteristics of our surface waters? Yes. A very typical feature is the strong coloring. I hope you can see it to the left in a rapid. You see the water, it's yellow, brown. And that is quite a typical feature of waters here up in our latitudes. It's colored. It's really brownish, yellowish. They are sometimes called black waters. They are not black, but the visibility through these waters is so low, so you can hardly see anything. Perhaps you can imagine here, you can just see 10-20 centimeters because of the strong coloring. Not all streams, not all lakes are highly colored, but a lot of them are very strongly colored, like this. And this coloring can reach even out in the estuary. So here I'm on a boat in the sea, basically. This is basically the Baltic Sea. It's quite far out in the estuary, and the water is still really yellowish and brown. Of course, the seawater is absolutely clear here, but it's a lot of river water coming into the sea, which is colored. So we get this kind of coloring. Anybody who has an idea what is causing this? Why are these yellowy? I mean, yellow waters.
Algae?
No.
Bacteria?
Sorry?
Bacteria?
Bacteria? No. No. Nobody knows. Have you even seen these colored waters? Okay, then I can say it's caused by humic substances. So these are organic molecules, which means they are composed of carbon, oxygen, hydrogen. They are complex and variable, and they are quite small sized, mainly of colloidal size. That means that they pass through these filters, 0.45 micrometer. That is the filters we use to separate out the particles from the water. They pass through these filters, so they are really small size. You can say that they are dissolved in the water. So it's not particles or bacteria or anything like this. It's basically molecules, organic molecules. And these humic substances are coming from the soils. To the left is a histosol. That is basically peat. Perhaps you know, but that is or they can be quite thick. They can be up to 2 meters thick, and it's more or less 100% of partly degraded organic material. So it's humic substances and other kind of degraded organic matter. And here is a humus horizon in a forest soil. It's a bit thinner. It's composed of roots, degraded organic matter, and also some geological materials. But to make it simple, these humic substances are derived from catchment soils, from organic rich soils in the catchment, and they are leached out into the streams, rivers, and even into the sea. And these soils are mostly occur in the forests. And we know the forests in Finland at least, and in large parts of Sweden, look like this, extensively ditched. And this has, of course, increased the leaching of a large number of components, including the humic substances. Because if it wasn't for the ditch, of course, the soils would be more intact and they would stay there in wetlands. But now when so much has been drained, it looked like this. Of course, these humic substances can go from these soils and into the water, and we get this very nice colored water. But it's important to stress that it's a natural phenomenon. Ditching activities have increased the leaching of these, yes, but it's a natural phenomenon. They have been there, I'm sure, for thousands of years and even more. It's a natural phenomenon. Where there are organic rich soils, like here up in the north, humic substances will be leached into the surface systems. So, some of the features of humic substances, as I already said, they are the soluble organic fraction of organic rich soils, and they are therefore leached and transported down through these systems. And when we want to analyze these, we normally measure the dissolved organic carbon, which occur then in concentrations of 20 to 50 milligram per liter. When it goes below 10, then the water starts to be clear, like in the sea, and so on. And this last one is quite an important feature in the context we are now. These humic substances have a high capacity to bind metals, including several radionuclides, such as uranium, thorium, radium. And this, of course, can enhance the mobilization and transport of these metals. So they are giving the waters a color, which somebody thinks is nice, somebody don't like it at all. But they have an impact, especially when it comes to transporting other, because they are quite large organic molecules with high capacity to bind metals. And this, of course, can enhance a metal like thorium and radium, may be quite insoluble, immobile, but if they bind to organic substances, they can travel large distances and enter ecological important systems and so on.
Are they in solution with the water, or are they colloids?
Sorry,
Are they're soluble?
Yes.
Okay, so they're not colloids. Okay.
Yeah, that is the thing. They are molecules which are dissolved, the humic substances. It's not particles, so they are not going to be deposited easily as on the bottoms. Mm-hmm. They are in true solution, more or less, dissolved as ions, so they can travel quite long distances down the aquatic systems, and they can pick up metals like radionuclides, and that means that as the humic substances travel through the aquatic systems, also all these metals which are bound to them. There are also a few other characteristic features of surface waters here up in the north, but these are not easily visible, like the coloring, the humic substances. So in order to present these, I will use the Geochemical Atlas of Europe, which is freely available on the internet. It's warm here, isn't it? But you have all the windows are open, aren't they? Oh. We have to live with this at 59 degrees north. Okay, but this atlas contains several kind of materials like soils, sediments, and it also includes stream waters. So there are about 800 streams across Europe in this map, and these streams were sampled once, and they look, here are 4 examples. Of course there are 796 more, but these are examples. Quite small streams, of course, can run through farmlands, hill, mountainous areas, and we have them in forests, so distributed throughout Europe. And these were, as I said, sampled once, analyzed. And of course one can come back later in the future and sample these same streams again and see if something has happened when it comes to the chemistry of these surface waters. So here is then a map of pH. Hope you can see something. But let's see, it's 800 streams, each appear as a circle. You can see a number of circles here. It's 800 circles if we start to count. And the size of the symbol, that tells us the pH of this stream. So if it's a small symbol, it's a low pH, below 6, and if it's a large symbol, it comes up to nearly 10. So each circle is one stream, and there is an indication of its pH. Now you also see colors here, and that is actually an interpolation from the real data. So in an area where there are many small circles, it will become red, low pH, which is the color of low pH. And in areas with a high frequency of large circles, will become blue. That is an area where the pH is high. So of course, Olga, the door. It helped quite a lot. Yeah, it helped. Yeah. So what was I about to say? Yeah, so if you are a scientist or something or want to look into detail into this, of course you look at the circles and all the data in detail. But if you just want to have a quick overview, an overall idea of what the pH distribution is, the colors are quite good, aren't they? Because you can very, very rapidly see that there are different areas of red and blue areas. And of course in this map we see red. Here is where we are now. There is some red areas here in Portugal and Spain and in the middle of France. But otherwise, much higher pH over the European continent in general as compared to here. So in the Nordic countries, the pH of the streams are low. That is another characteristic feature. We have the coloring, but we also have low pH. And you can see it's really very strong pattern. So there must be an underlying reason for this. And of course there is the reasons for the low pH in our streams. First of all, it's the bedrock. And you have heard about that. The bedrock in this part of the world is composed of mostly of granitic bedrock. Granitoids we can call them. It's crystalline bedrock. And this, as you might have heard, these and the soils that develop from them are not easily weathered. That means that they are not reactive towards the acid, the protons. So when the protons of the acid come in contact with this bedrock and the soils that develop from them, the reaction is very sluggish compared to, for example, limestone, which reacts very quickly with the acidity. So basically a very slow reaction between this bedrock type and acidity. And that is the same as a poor buffering capacity. The bedrock and the soils have very low capacity to consume the protons. But that is of course not, these are not producing the acid. These are just, if acid is produced, they will not have the capacity to neutralize it. So it's important to make this difference. The acidity itself comes from the humic substances. Here we go again. The humic substances are mainly composed of what we call humic acids and fulvic acids, two kind of organic acids. And these are weak acids, so not strong, but weak. But still, they are acids, they produce protons, and when they release the protons, they are not reacting very fast with the bedrock and with the soil, which means that they stay in solution, and that is the same as a lowering of the pH. So again, the humic acids play, or the humic substances play a role here. So they are very important for the surface system here up in the north. Of course, there is some atmospheric deposition. But as you may know, the rain, snow here was very acidic in the 80s, in the 90s, but the acidity in the rain has dropped considerably. So the pH of the rainwater today is much higher than it used to be. So only a small contribution. And of course, if this would be a main parameter, we would not have the acidic waters here up in the north. They would be more on the European continent. So it's mainly the humic acids, fulvic acids, produce the protons, and the bedrock which cannot neutralize it. So, low pH waters. I can also say here that the pH of the waters here, it's varying very much over the year. So that would be another factor to consider in science and so on. The general pattern is fully true here, that we have overall acidic waters here, but the pH can vary quite a lot. It's lowest actually in spring after the snow melting, and when it rains a lot, then the pH typically drops. Whereas on more dry periods like we are in now, the pH tends to rise. But that is another question. We don't need to go into that here. The important thing is that overall the pH is low up here. And here are two other maps of aluminium and of iron. Two metals, especially iron, very important for the ecology, it's a nutrient. But both of these can also be toxic, especially aluminium. That is, I mean, that is not an element that biology needs. Iron, on the other hand, yes, it's a nutrient, but it can also be toxic if it occurs in too high concentrations. So these two elements are quite interesting to study in any hydrochemical investigation. And here we see again the same. Now on these maps, the large symbols are marked with red. And again, Northern Europe, red, both for iron and aluminium, which means high concentrations. And as you see, much higher concentrations than in the rest of Europe. So another typical feature of the surface water up here, high concentrations of these two metals and also a number of other metals. So why is this? The reasons are, in any area where there is granitic bedrock and soils that develop from it, there is quite a lot of iron and aluminium in the soils. So it's about availability. These metals occur in the soils. But that is not enough. Low pH. When the pH drops, a number of the solubility of a number of metals increase. Iron and aluminium and many others. So they are related. You remember the low pH up here? Low pH, and that increases the mobility of these metals. So we get higher concentrations in solution. And one more thing, the humic substances. As I said earlier, these have high capacity to catch and transport metals, including iron and aluminium. So now we see how everything goes together. Humic substances are leached, color the waters. They cause a drop in pH. A drop in pH increases the solubility in soils of metals, so we get them into solution. The humic substances pick them up and transport them downstream. So everything goes together, and humic substances are a key player here. So we go to two other metals, the last slide here. Now it's calcium and bicarbonate, two other elements of common interest in hydrochemistry. And I just show you these because they have a totally different pattern. Blue areas, which means low concentrations, much lower than over the continent. And that is because limited occurrence of limestone. On the European continent, a lot of sedimentary rocks containing limestone, which cause mobilization and leaching of calcium and bicarbonate. And also the low pH of the waters, they cause a degassing of the bicarbonate. So also pH has a small effect here. So just to summarize, the stream waters here up in the north, we have said the low pH, high organic carbon, high iron and aluminium, low calcium and bicarbonate. Of course, a number of other features for trace elements and so on, but these are the main things. And all this is relevant for understanding and predicting radionuclide transport and behavior in the surface systems. So even if all who work now with the repository of the nuclear waste are mainly focused and interested in depth of 400 to 500 meters below the ground, it's very important to understand and study the surface system, because only when, not until the radionuclides potentially reach the surface, they will be harmful to the ecology and ultimately to us. That was my first part. I think we can take a break and continue at 10 to 4. All right.
Well, you've only heard us say it.
Let's continue. So now when you know everything about the chemistry of stream waters, we can go on and share a few things when it comes to the chemistry of the groundwater in bedrock fractures. And the reason why we have groundwater in bedrock is that it's fractured. You see all the fractures here. If there was no fractures, the bedrock would be very dry and very little water. And actually, when the Swedish Nuclear Fuel and Waste Management Company chose their site for deposition of the radioactive waste, they chose Forsmark, which is a little bit north of Stockholm, and they did not choose Oskarshamn, where we are now. And a main reason for that was the fracturing of the bedrock. The bedrock in Forsmark is less fractured, it's drier than here when it's extensively fractured. So the groundwater in the bedrock fractures can have several different origins. Of course, precipitation. And here in the north it means rainwater and snow meltwater. And together these are often called meteoric water. Of course, when it rains, when the snow melts, this water can penetrate into the fractures, like here, directly into the fractures. In areas like this, where the bedrock is exposed, or there is a very thin soil cover. So rainwater seep into the bedrock fractures. At other locations, this rain and snow melt water first percolates through the soil. Of course, in many sites there is quite thick soil cover, so before the rain and snow melt goes into bedrock fractures, it will have to pass through the soil, which it can do because it's unconsolidated. It's a lot of small grains. And when it percolates through the soil, there will be reactions between the meteoric water and the soil minerals, and this means that the rainwater picks up some constituents, some ions, cations and anions from the soil before it goes into the bedrock fractures. So this water, in the context when we work and work with deep groundwater in fractures and want to know the origin, we can sometimes call this the altered meteoric water, because it was altered when it passed through the soil. The sea, of course, it's easy to imagine that seawater can be pushed into bedrock fractures. That is quite easy to imagine. And this can also occur on coastal plains like we are now, especially, or as a result of, I should say, geological and climatological phenomena. For example, after the last ice age, the land here was pressed down 100, 200 meters, and the sea flooded large areas. And of course, at that times and those times, the seawater comes over the land, like here, easy to imagine, and penetrates into the bedrock fractures. And then we have continental glaciers. Yes, we don't have any of these glaciers here right now, but we used to have a lot of them. And the last one melted away 10,000 years ago. And when thick ice covers are melting, they are able to push this meltwater quite deep into the bedrock fractures. So such water we actually do here under our feet right now. Glacial meltwater. It penetrated about 10,000, 20,000 or 30,000 years ago when the last glacier melted. So this is a very characteristic feature of the groundwater residing in the bedrock. It can have various origins. This is not of any interest when we work in the surface system. Then it's only rainwater and snow melt water which goes through the system in days or weeks. Here we talk about totally different time scales when we come deep into the bedrock, and we can have waters of highly variable origin which penetrated during various time periods. So just to summarize here what we have right here in this region in the bedrock fractures. As I said, precipitation, that is modern fresh water. Do you know what fresh water is? Fresh? Yeah, it's non-saline water basically, so it's not saline, it's non-saline. You can drink it. And it's modern, I say modern, it's quite recent. And then glacial meltwater, old fresh water. And that came in to the bedrock fractures when the ice cover melted. Seawater, I say modern and old, because the sea was always there. Seawater can have penetrated into the bedrock fractures now, 1,000 years ago, 500 million years ago, or whatever. The sea was always there. And it's brackish. In the Baltic Sea, it's brackish, in between fresh and salt. And then there is also something else. Some very deep waters, starting at about 400 meters depth and going perhaps down to tens of kilometers. We don't know for sure how deep. The deepest boreholes we have here go down to nearly 2 kilometers, not really. But at least to those depths we have, and the further we go down, the more saline this water tends to become. So it would be very interesting to go down to 5 kilometers or something here, but that costs a lot of money. And these are actually old and very saline. Also hard to know how old they are, but I would guess the deeper you go, the longer they have been there. Some have been dated to 1.5 million years, but they may be older, perhaps 100 million years. Who knows? So this is a very characteristic feature, the age differences, the different water types. This is something totally unknown for us who normally or previously worked in the surface system when we talk about days and weeks. Here we talk about something totally different. And if we don't take this into account when we want to understand the groundwater in bedrock fractures, we will come nowhere. Now, these different waters can actually be identified by quite simple measures. We can measure the chloride concentrations, and that will define the salinity. You know, chloride, that is the main ion in seawater. And normally chloride correlates very well with salinity. So the more chloride, the more saline is the water. So in the fresh water that we drink from the tap here, that's very low in chloride. But the seawater has high chloride, and the brines, some very, very salty water, have very high concentrations of these, and iron. And another very valuable variable in this context is the ratio of oxygen 18 to oxygen 16 of the water molecule. You know water, H2O, basic chemistry. Every water molecule has 2 oxygen. And it can be oxygen 18 or oxygen 16. That is 2 different isotopes. And this varies from water type to water type. And it's called the delta 18 oxygen, and simply we call it 18 oxygen. And I'll just shortly show the principle here. Increasing chloride concentrations. Of course, the waters with lowest chloride are the fresh waters, as you would guess. The glacial meltwater and the rain and snow. And then we come up to the brackish seawater and the old saline water. So actually, just by measuring chloride or salinity in different fractures, we can get a first idea, of course. Is this fresh? Is this saline? But we would not be able to separate these two, and these can also be quite hard to separate only because they can have quite similar chloride concentrations. So then we also take in the oxygen 18 increasing ratios, higher values. So the lowest values, which means that the highest relative proportion of the light isotope, that has the glacial water. It can have down to -20, -30, so very low values, which means it's enriched in the light oxygen. And here we have intermediate values, and the seawater has the highest. So now we see if we start to combine these two. Okay, we couldn't separate these with chloride, but we can with the oxygen. That one and that one. And if we couldn't separate these with chloride, we could with the oxygen ratio. So with these only two variables, we can go in, measure these, and get a first quite good idea of what is the origin of a groundwater in a specific fracture. Of course, in reality, as you would guess, there is some mixing of these waters. No natural system is so pure that you would have here is the seawater, the old saline water, and the meteoric water, and here we have seawater. Of course, there is also mixtures. But still, we can, in some boreholes, have quite pure waters or end members. So I will show an example. SH262V Hard Rock Laboratory. View from the air. Now, very nice site in the forest, close to the sea. I guess you haven't been here as yet. My office, I guess you want to know where that is. Ah, it's there. And you can have some walks in the lunch here around this nice area. So it's a very beautiful area from the air. The archipelago of Oskarshamn, very nice buildings. And this is a bay, so the sea expands here. And you come over to Finland and Russia and Baltic states. And then if we go underground, it can look like this. A nearly 4 kilometer long tunnel extending to nearly half a kilometer below the surface. Of course, you will go here later during the course. Myself here to the right, and the PhD student here doing some activities here in the tunnel. First time when I came to the tunnel, I was a little bit surprised because I thought, what is this? It was nothing, it was just a tunnel and some tubes. Where are all the equipment? It's a laboratory. I didn't see anything. And that is of course true, because things are not going on in the tunnel. We just drive the cars. The activity is going on inside the bedrock. So mostly it's a tunnel. Of course you can see something, but what I'm doing, groundwater and chemistry, you cannot see anything. You could see some boreholes coming out somewhere, but it's just a tap in the wall and the boreholes go straight in. Anyway, if we look in some more detail, it looks like this. Here we have the nice buildings, and you can go by an elevator down here to nearly 500 meters. And here you see the Baltic Sea and the island. And of course then underground, we go underground, we have the tunnel. It starts up here. It's a ramp, goes down, and then it spirals down here to nearly 450 meters. And as I told you already, that in the tunnel, when we do hydrochemistry or we sample water here, we are not sampling in the tunnel. We are sampling from boreholes that goes from the tunnel wall or from the surface. And it looks like this. This is not in the handouts anyway, this one. So you see here is now a fracture. And here is another fracture. And they have water conducting. These fractures are more or less filled with water all the time. And here is a borehole from the surface. And you see the principle. The borehole hits the fracture. And then there is a lot of equipment in this borehole so that water can be pumped up to the surface. So this is the principle how we sample the. It's totally different to the surface environment which I used to work with. Just go out to a stream and collect some water in whatever bottle you have, more or less. Here it's a quite complicated equipment and you have to pump it up to the surface. Here is SH262V hard rock laboratory now. Here is the tunnel and you see the wall here and it's a borehole going here and the same principle. Water comes through the fracture into the borehole and it can be collected in a tap in the wall of the borehole.
Isn't it counterintuitive to be putting a borehole in the middle of a fracture?
Sorry?
Isn't it counterintuitive to put a borehole in the middle of a fracture? I mean, with the spent nuclear fuel, though, wouldn't it be at risk for breaking itself?
But this SH262V hard rock laboratory, we are not going to put any nuclear waste there.
Okay.
No, that is, so this SH262V hard rock laboratory, as you will learn later, that is a research laboratory. It was not intending for repository of nuclear waste. But it's different in other countries. In other countries you do both research and you plan to deposit the waste at the same site. Not in Sweden. This is a research laboratory. No waste was ever intended to come here. That's why it's boreholes all over the place. And we can hit as many fractures as we want to, because there will not be no waste here. So here, this is just to investigate this water. And when we close the tap here, of course, the water will not, it's not like water is coming here all the time, it's closed. So it's only when we open the tap, when we drain water from the fractures. Otherwise, it's more or less natural.
I mean, the diagram looks like very nicely, but when you are making a borehole, is there a, like, is the borehole also possible to make the fracture more larger?
Yes, yes, of course it can. You never know when you drill a hole in the rock. You cannot be fully sure what is happening. And you can open new connections. Perhaps there, so you really don't know what. And that is a very good question. And that is why it's always tricky to work in these settings, because we can never see exactly what we are doing. And when we make a borehole like this, of course we change the system a little bit as well. We affect the hydrology, we can affect the chemistry, and we can above all affect the microbiology, as you will hear more in a minute. So you are absolutely true. It's when we dig a hole, we destroy the system. So we are never working in a fully pristine environment. We cannot be sure that this is exactly what it would be in nature, because we made a borehole, we pumped out the water, but that is the best we can do. This is basically state of the art. That is the best we can do. But it's a very good point. But this is so then how the water is collected. And now we look at this picture again, and you see all these boreholes here, marked here with the names, tricky names. And the water in each borehole is marked with a color. And these colors indicate the origin of the water in that borehole. So you see some green dots here, which is meteoric groundwater, not so surprising, shallow fractures under the island. When we go down, it's a lot of blue stuff here also, and that is groundwater coming from the sea. Marine or sea groundwater. So it's fractures going from the sea into the bedrock, and seawater is penetrating through these. And we measure seawater down here. And when we continue in the spiral, we get a lot of red boreholes. And this is the old saline groundwater. It's more saline than seawater. Origin, more or less unknown. Age, more or less unknown as well. It's saline, which means it's heavy, so it sits very stable. There are basically no forces to push this deep, saline, heavy water away, so it just sits there. And then there is also a lot of white boreholes here, and that is mixed. It's not possible to define any dominating origin in these. Like here, where we had the dominance of seawater, dominance of meteoric water, the red, the dominance of saline groundwater. But in the white, we measure chloride, we measure oxygenating, we measure a large number of other variables as well, which I didn't show here. But despite this, it's not possible to separate and to distinguish which type is actually dominant. So it's a mixture of two or several.
How are you going to investigate the water in a repository? Because you cannot drill a borehole wherever you like. So is a standard method to sampling the water in the bedrocks? Previous
yes, it is. It is, yes. Of course, there will be much fewer boreholes when they make the repository. I am not fully sure of what they are going to do. I know they are right now planning for these activities, how to sample, what to measure. So I would say it's not really, I don't think it's fully clear. This is all what I show is from the research laboratory, where they made as many boreholes as they could afford just to understand how the system works. So here we the SKB have learned the system. They know basically how it works. And that is of course very helpful when they make and build a repository at another site, which is very similar, except that it's a little bit drier, so it's fewer fractures. At least they think, because as you say, they haven't made so many boreholes because they do not want to make. It's not a good idea, as you pointed out. If it's a lot of boreholes, I mean, yes, it's a good route for radionuclides if it's too many. Yes, but to understand the origin of these waters can be valuable for many different reasons. And I'll show you one thing. And that is cesium. You know cesium. That is a metal in the periodic table of the elements. And a feature of these groundwaters is that they have high concentrations of cesium. And that was quite unexpected. Many of these boreholes have high concentrations of cesium. Now remember, this is cesium-133. That is a stable isotope of cesium, and it has existed on the planet ever since it was formed. This is natural cesium, but it occurs in high concentrations for some reason. A little bit unexpected. Now cesium is of course always interesting in terms of radioactive waste, because there is this cesium-137, and that has a half-life of 30 years, and it's highly radioactive. And it's one of the key components in nuclear waste, and it was spread of course in the environment from the Chernobyl nuclear accident. I sometimes work with sediments, and then I like this isotope because it's a fantastic time marker. When we collect sediment cores here up in the north, we measure the activity of cesium-137, we get a peak, and we know that exactly at this depth we have 1986. So it's a very, very valuable time marker. But it means that still we find these in high concentrations, in relatively high concentrations, measurable in the environment.
You remember the energy of cesium 137? We talked
61
today. Yeah, sorry? 61, yes. Kilo electron.
So now we come to Espe-Harrock laboratory, cesium concentrations in the fracture groundwaters. You see the depth here from the surface. The deepest sample is from 800 meters. And each dot represents one measurement. And now look at the cesium scale. It goes from 0 basically to 6 microgram per liter. Microgram per liter. That sounds quite little, doesn't it? And it is, because this is a trace element. And they always occur in high concentration, low concentration. That is why they are trace elements. But we can compare, for example, with stream waters in Europe, the Geochemical Atlas of Europe, which contains 800 stream waters. It has a median cesium concentration of 0.006 microgram per liter. So the highest cesium concentrations in the groundwater are 1,000 times higher than the median cesium in stream water. So it's high for some reason. Now if we look in some more detail, another thing you can see that there is quite poor correlation between cesium concentration and depth. The lowest concentrations are at shallow depth, but after that there is no correlation with depth. That is one thing one always checks when you look at systems like this, when you have unique data from the surface to nearly a kilometer, which we have here at this site. I mean, it's absolutely unique data. To have chemical data from the uppermost kilometer, it's not like anything anybody have. It's really unique. So I always check, are there any correlations with depth? For cesium, there is really no one. What we can see, however, here is that the cesium concentrations are correlated with the origin of the water. The green symbols, that is the meteoric water. You see relatively low concentrations. And the same with these light blue, which is the glacial meltwater. Intermediate concentrations overall in the mixed, the white. And then the highest concentrations in the blue, which is the seawater origin, and in the red, which is the deep saline old groundwater. So the cesium concentrations are overall high in the fracture groundwater, but particularly high in some when the groundwater is of some specific origin, the seawater origin and the old saline. Now one could think that, okay, cesium is correlated to the age of the water, but it is not, because we know that this seawater, or the groundwater with seawater origin, we know that this seawater penetrated less than 20 years ago. And we think that this red, the old saline, is millions of years old. So the cesium concentrations is not correlated with depth. Now take the first case, this blue one. This is groundwater which came from the seawater, marine groundwater. Now we could of course hypothesize, okay, so the seawater contains cesium and it was brought with the seawater into the bedrock. But it is not. The seawater contains 0.29 microgram per liter cesium. It's down here. So the groundwater here with the marine origin has 10 times more cesium than the seawater. And this means that when seawater penetrates into the bedrock fractures, it very rapidly picks up cesium from somewhere, and the concentrations increase very rapidly. And we see that this happens very fast. Within a couple of years or faster, it picks up cesium from somewhere. And what we think is happening here is an ion exchange reaction. There is cesium attached to mineral particles, to the surfaces of minerals in the bedrock fractures. And when the groundwater, when the seawater comes in, it has a lot of potassium ions and ammonium cations. And these particular ions have a high capacity to exchange with cesium in some specific cation exchange reaction. So what is happening when the seawater coming is that potassium and ammonium become attached on the mineral surfaces, and cesium goes into the water. So it's an exchange between cations coming in the water with the cesium cation on the surfaces of some minerals. And this, of course, might have some relevance also in terms of leakage from a repository. If cesium is leached, we will know that any marine water which has intruded will have quite a high capacity to keep and maintain cesium in solution. And what are we have high cesium concentrations also in the old ones, and that may, in addition to cation exchange, this may simply be a very long time of weathering over millions of years. So minerals which contain some cesium are being weathered over long time scales, hundreds of thousands of years, millions of years, and when the time goes by, cesium is via that process released into the solution. So I'll just sum up here the specific features of the fractured groundwater of variable origin and has a large range in salinity, as I showed. This is completely different to most surface environments. The range in origin, the range in salinity, and high cesium concentrations when the water is of marine origin or very old. Of course, we could list some other metals as well, but I took cesium as an example because it's interesting in this context. And then a few other features also of this water, which I haven't mentioned as yet. And the first one, which makes it very different to surface waters, is that it's reduced, which means that there are no or very little oxygen, dissolved free oxygen in the water. This means that iron exists as 2 instead of 3 plus, manganese as 2 plus instead of 4, and sulfur exists partly as sulfides. So these oxidized species here to the right, which we have in the surface environment, are being reduced to other valencies. And this occurs, and this is done by and carried out by microorganisms, the topic of the next presentation. And another very typical feature here, as you just heard, we have acidic surface waters here. The precipitation is a little bit acidic. Everything is more or less acidic in the surface environment here, but not the water in the bedrock fractures. That's always high, near neutral to slightly alkaline. And this is also partly an effect of the activity of microorganisms. And finally, which is also a little bit relevant considering what I told you earlier, the concentrations of humic substances are overall very low in these waters. So they are mostly clear, very clear and nice waters, look like seawater. Except for a few very shallow fractures which are of meteoric origin. So thank you for listening.
Questions? Yes.
So, towards the end, you mentioned this high concentration of cesium and possibly the reason being ion exchange. So, the question is, why this cesium selectivity in ion exchange? Is this happening with other metals as well?
Yes, it's quite interesting. Yes. We are not sure, but it's probably related to something that is called frayed edge sites. That is a specific sites on phyllosilicates, which are very specific for cesium. So cesium bind quite strongly to these. And they can be displaced only if there is high concentrations of cations like potassium and ammonium. They have capacity actually to displace cesium from these sites, where cesium normally sits quite strongly. We haven't been able to prove this, but we find this as the most likely explanation that we have, because we know we have quite high cesium concentrations in some of the coatings on the fracture walls. So we know that the cesium is there, and probably as we have this kind of high concentrations rapidly after seawater intrudes, it must be a cation exchange. It cannot be weathering. It must be cation. So that's why it seems most likely that this is what is happening. But it's sort of a guess also.
No more questions? Manson, you look like something else. Okay.
Or could we could have a couple of questions if there are some left after marks?
Yes, after mark.
Yeah.
So we take 10 minutes break. Okay, 10 minutes.